Alrighty, welcome back, boys and girls. It's your main math man, Shane, coming to you live from Summit Academy. And in this video, working on that unit number 8, still talking about those areas and side lengths. And so on the first part, what I want you to do is I want you to think, pair, and share. So work with your partner on this one. It says notice and wonder. It has a square and 4 triangles. What do you notice and what do you wonder about these pictures? Some examples you could say are like this. I could say something that I noticed for these two is this. So let's say if I'm looking at this picture, I could say, well, I have a square with 4 right triangles. Where on the other one, I could say I have a square with, this is a square with just 4 non-right triangles. So that's just a simple observation. Try to come up with what you think or what you wonder. All right, on the part underneath it, still working with that idea in our head that we're working with our Pythagorean theorem. It says both figures shown are squares with a side length of a plus b. And so that's talking about this side length here is just a plus b. So it says, notice that the first figure is divided into 2 squares and 2 rectangles. So we have these 2 squares here, and that means that the other shapes are going to be those 2 rectangles. So it says the second figure is divided into a square and 4 right triangles. So that's that shape G. So let's say the hypotenuse of these triangles is going to be that side length C. So that means this is C, this is C. And so that means that the area inside of that square would be C squared. So it says what's going to be the total area of each figure. And so what we can do is this. Again, similar to when we worked with that distributive property, we can multiply these 2 side lengths together. So if this side length is A and this is A, that means that this is going to be A squared. Similar idea, if this is B and this is B, that means that this is going to be B squared as well. However, with these rectangles, again, to find the area, just the side lengths multiplied together. So that means this product is going to be AB, and this product is going to be AB. Even though we don't have any numbers, that's okay. We can use those variables for a general idea. However, with these triangles, how does that work again? Well, it's going to be the product of these 2 side lengths divided by 2. So this is going to be AB over 2 for each of these little triangles. So I have AB over 2. And so it says find total area of each figure. So that's going to be what? So we have for the first one, it's going to be, let's say is this F? So this for F, we're going to say it's going to be each of these added together. So I have A squared plus AB plus AB and plus B squared. And we're saying, should that be equal to the side length, or sorry, the area of the other square? So we're trying to figure out, are both of these squares or figures F and G the same? So then this part we already did because we found the area of each of these. And what we can do is we can add up the area of the 4 regions in figure F, the one on the left, and set the expression equal to the sum of the areas on the figures in figure G. So then we can rewrite it like this. So we're going to say if we have, this is the area of F, and we can say if G is this, so let's say G is going to be, well, how many triangles do we have? So we have 1, 2, 3. We have 4 of those triangles. So I have 4 times A times B over 2 plus C squared. And what we can do is we can kind of see some similarities and differences between this. So let's see like this. If I simplify this, this would be the same as, this is going to be equal to, I'd have 2 times AB plus C squared. And what I can compare is, well, if I look at these 2 terms in that figure F, that's also going to be 2AB. So I can say F is the same as A squared plus 2AB plus B squared. And if we know that these total areas are the same, I could say that hey, if I compare these 2 amounts, I say 2AB and 2AB from each figure. If I took those out, I would say that, well, it kind of creates our Pythagorean theorem. So we're saying that in the main idea that we're trying to get is we have that A squared plus B squared from our figure F, so these two squares. We're saying, hey, if we add those two together, it should equal our C squared, so the remaining amount on the right side, which is the same thing as our Pythagorean theorem. So make sure you can kind of see how that's a proof of piecing those together. Not my favorite proof, but that's okay. We're trying to get some different ideas with that. Okay. Again, feel free to pause, rewind, replay, ask questions as needed. So now on the third part, underneath of it, it says let's take it for a spin. So we're going to use that formula that we did in previous ideas to find that missing side length. So anytime it says unknown, that's what we're trying to solve for. Again, make sure you can set up like this. Find your right angle. So we're going to say, hey, there's my right angle. Across from that right angle is going to be my hypotenuse. So I label that as my hypotenuse. And so I'm going to say, well, I know my equation for this is going to be a squared plus b squared equals c squared. And I can say, well, if I have the side lengths or the legs, I know that this is going to be 2 squared. This is going to be 5 squared. And our hypotenuse is just x squared. And so I'm going to use those to find my perfect squares. So I'm going to say 2 times itself is going to be 4. 5 times itself is going to be 25, and we know that we're trying to solve for x squared. So these two together is going to be 29 equals x squared. Make sure you can take the square root of both sides. So we take a square root, and we can say that x squared, or sorry, x, that side length, is going to be the square root of 29. If you want to give that decimal amount, you can say it's going to be about 5.38. Either one would totally be fine. And I know that works out because that hypotenuse should be the longest side of each of these side lengths. So I know that it had to be more than 5, which it is. So now on this one, so let's say on this one, pause for your turn. So try this one out. Again, same idea. Set up your equation first, plug in your values, and now you're going to solve for that missing side length. All right, underneath of it, similar setup, we're trying to find the lengths of the unlabeled sides or the missing sides. So same kind of setup I'm going to do, again, always use, just like we did on the last set of nets, we had labels, we had our formula or our equation, we substitute, and we solve. So make sure you're following those steps when you're trying to find for that missing side length. And so again, same idea. I'm going to say, well, where's my right angle at? It's right there. Across from it is that missing side, which ends up being the hypotenuse. So we're going to say this is going to be our hypotenuse, is that side x. So that means if I go to have my formula, I'm going to say I have a squared plus b squared equals c squared. I'm going to say I have 2 squared plus 6 squared is equal to x squared. Make sure you can simplify. So I'm going to have 2 times itself is 4. 6 times itself is 36. I'm going to say that equals x squared. Going to be able to combine those two together. So I'm going to say this is going to be equal to 40, which is equal to x squared. Use those inverse operations to get x by itself. So take a square root. Take a square root of both sides. And I can say that x is going to be equal to square root of 40, which is going to be approximately, let's say, about 6.32. So find that missing side length, know that it has to be the largest of those 3 sides, and be able to solve for x. So now on that third one, same idea, your turn, try using those same steps as before, and try to solve for that missing side length when your 2 legs are 6 and 8. On the back, similar to what we did before, it says one segment is n units long and the other segment is p units long. Find the value of n and p. So it tells you that each of those grids or each of those squares is 1 unit around or 1 unit space. And what you can do instead of having to draw that tilted square like we did before, what you can do is you can draw the right triangle. So draw the right triangle. And so you're going to say, all right, if it looks like this, this is my side length that I'm looking for is n, but I can kind of draw it like this. So let's try, I have something like this. So I have that right triangle. What are my side lengths? Well, I know that up and down is 3 and left and right is 1. And so what I can do is I can use that Pythagorean theorem to solve for that missing side length or that side length n. So I'm going to use my Pythagorean theorem as always. So I have the equation first. I have my labels. Then I'm going to substitute. So I have 1 squared plus 3 squared is equal to n squared. Be able to simplify and solve. So I have this is 1 times 1 is 1. 3 times 3 is 9. And we bring down n squared. And so that's going to be 10 equals n squared. So that just means that n is going to be equal to the square root of 10, which is going to be about, let's say it's going to be between 3 and 4. So make sure you can say, let's actually say that. So it's like between 3 and 4. So that way you can get some practice with those two consecutive integers. So same idea, draw your right triangle. So let me draw it like this. Let's say if we have one side length is 4 units and the other side length is 3 units, make sure you can use that formula to be able to set it up. On the next part, it has this. So for number 2, it says use the areas of the two identical squares to explain why 5 squared plus 12 squared is equal to 13 squared without trying to do any calculations. So it's very similar to the front side, and what we're trying to do is we're trying to prove to see if that Pythagorean theorem works. And so what you can do is you can kind of piece it together. Notice how it has the side lengths there for you, but if you want to, you can kind of write it like this. So I'm actually going to use those areas or use the same strategy as I did before. So I do 5 times 5 is 25. I do 12 times 12 is 144. And then I can find the areas of the smaller parts. So 5 times 12 is 60, which is the same as the other rectangle. On our figure to the right, we can say same idea. If I take 5 times 12 divided by 2, each of these triangles are going to be 30 units. So I can say each of the areas of these triangles is 30 units, and we have 4 of those triangles. Then I can say the area inside of that tilted square is going to be 169 because I have 13 times 13. And so now it's trying to prove this. So I can say, well, same setup as before. I can write out the values I have. So I have on my left triangle, I have 25. Let me actually write it over here. I have 25 plus 60 plus 60 plus 144. And then on the right side, I can say, well, is this equal to my triangles that I have? So I have, is this equal to 30 plus 30 plus 169? And what I notice is, hey, if I add together these two terms of 60 and 60, that's going to be 120, which is the same as 4 times 30. So each of these is 120. So those can cancel out. And so what I'm saying is this. I can bring down, I can say, well, I have 25 plus 144 is equal to 169. And we know that 169 is equal to 169. So that gives exactly what we have, because this is the same as 5 squared, this is the same as 12 squared, and this is the same as 13 squared. So as long as you have that logical series of steps, you'll be good. For number 3, it says each number, be sure to label each number between two consecutive integers. So what does that word mean again? So when we say the word consecutive, just think back to back. And so, for example, we could say something like, Wednesday and Thursday is an example of back-to-back days or consecutive days. So we actually already did that number 10. We said that was equal to, it's going to be approximately, we said that's about 3.16, which if I'm looking for those two consecutive integers, I have to have back-to-back numbers. So I'm going to say the pair of numbers that it's between is going to be 3 and 4. So I'll give you one more. So for example, if this is equal to or approximately 7.34, I know that the two numbers that it's between is going to be 7 and 8. So try these ones out on your own. Again, use that calculator if you need to, or you can use that list of square roots that I gave you in the previous day. All right, last couple ones towards the bottom. For number 4, it says, give an example of a rational number and explain how you know it is rational. So what I'm going to do is I'm going to give you the definition, and I want you to give me the number. So again, when it's rational, that just means it could be a ratio. So anytime any fraction would work for a rational number. And if you're looking at the decimal form, so the decimal either ends or it repeats. It has to do one of those two. If I'm looking at the irrational number, however, it is the opposite. So it's the ones that are not rational. So that means this: it must not end, it must not end, and it must not repeat. Must not, try that again. Say not repeat. So it must not do both those things to not be rational. Also, too, you should not be able to make it into a fraction, because otherwise that would be a rational number. So try to come up with 3 different examples for irrational numbers and try to give me one example for a rational number. And then lastly, at the very, very bottom, it says the Pythagorean is true for all triangles, it's true for all right triangles, it's true for some right triangles, or it's never true. Well, we know for sure that it cannot be these two because it's not true for all triangles, and it's not never true, so it can't be that either. So we're going to say it's true for all right triangles. So this is the one that you want to pick because it's only true, so only works for right triangles. So again, make sure you can pause, rewind, replay as needed. Again, use that calculator or that square root list as needed. And as always, super slam that subscribe button.